time, and we're going to start this next lecture that's mentioned here. And then, when I get to 35 minutes past, I will give out the exams, as I mentioned at the beginning today. Yeah. So here we're going to be relaxing one of the assumptions that we talked about. These practically could be combined as a single lecture. But we're going to be relaxing the assumption about uniformity that we've talked about. I'm not going to relax the assumption on independence. That's a more complicated thing to relax. But we're going to relax the assumption that says, for example, that all the 10 ratings had 1/10 of the people. We're going to talk about histograms. Okay, and this we already talked about at the beginning. The curve on the midterm, as I mentioned, is 0.9x plus 11, which, for example, maps an 82, an 83, wrong direction. Come on now, you can do it. Okay, so we've already talked about the answers, including the correction on that clustered answer, and I'm sure that there will be various questions. What I will emphasize is that there were times when people's answers weren't specific enough, and I'm sure there will be questions about whether or not the specificity was required. Specific answers got more credit than answers that were vague, and it is important to explain your answers. So anyway, we'll get in. So there are statistics that are in the catalog that help you understand things like how many different tuples are there in relation? How many different values of there are rating or some other column? What's the highest value and what's the lowest value inside this column? Those statistics are not kept up to date all the time on disk. They're not even kept up to date all the time in memory, although there's more work that happens now to try to keep them up to date in memory, even though they're only persistent periodically. And it is not critical. We have imprecise statistics, imprecise cost formulas, and the idea of the optimization isn't to figure out what the exact cost is, although it comes a lot closer than it used to. I'll go through three things. It used to be you wanted to avoid bad plans. The name optimizer makes it sound like I like counting 1 through 2. Number 1, avoid bad plans, still important. Number 3, the word optimizer seems to say you want to pick the best, but there is no clear definition of what the best is unless you tried all the plans, which you're not going to really do. If you feel bored, if a system feels bored, it might try some alternative plans and see whether or not that alternative plan might be better. There is a lot of that goes on now. That actually tries to check if some plan might be better than the one that it's currently using. It's bored, has the free cycles, why not? But the middle thing, which is important in Optimizer, is to find a good plan. Okay, and these days, a very good plan. So again, System R wanted to avoid bad plans. The name Optimizer suggests best plan, which is impossible really to define unless you check out exhaustively every plan for the current data, which will change. So the really idea is to find a good, or again, more likely these days, a very good plan for doing the execution. And we've had simplifying assumptions that we've talked about. Uniformity, which means, for example, if there are 10 rating values, we'll assume that 1/10 of the sailors have each of the ratings. And the independence of attributes, which basically says that if we have, again, a thing on rating and a thing on age, if 1/10 of the people have a given rating and 1/2 of the people have a given age range, we'll assume 1/20 of the people, 1/10 times 1/2, have both that particular rating and that age range, 1/10 times 1/2. It's not necessarily true. So some of the statistics that are kept are, what's the cardinality of each relation? If you have variable length things, how big are the tuples? How many pages are there inside the relation? And by the way, for those three things, cardinality, and if you have a row store, the size of the tuple and the number of pages, and if you have that and you also have an estimate of free space, you can figure out, several of these things from each other. For example, the number, if you assume there's no free space, then the number of pages equals cardinality divided by width if there's no free space. With free space, then everything gets thrown off a little bit. If you have an attribute that's indexed, it's not hard to keep track of the number of zinc values because, the index can help you figure that out. a little bit of work to do. But there are other ways that are done, including using sampling, by the way, to try to approximate the number of distinct values. Even when I was at System R, we had a student working with us who, based on some algorithms, some great universal hash functions that came from Carter and Wigman, that used that sampling method to try to figure out approximately how many different values there are in a column. How many different ratings are there? You might know that there's a constraint that rating is between 1 and 10, but there are all sorts of columns where you might not know how many different values there are. So there are all kinds of techniques to try to estimate the number of distinct values. Range of values, if you keep the low and high value, then you can use that as a basis of trying to figure out, if I know that age is between 0 and 99, then if I'm using uniformity, then I can assume that 1/10 of the tuples are between 90 and 99. Because there are 100 different values, there are 10 values between 90 and 99. By knowing the range of values, if I'm assuming uniformity, I can estimate range sizes. That is, that there are 1/10 of the ages are between 90 and 99. 1/10 of the tuples have age between 90 and 99. It's probably not true. It's one reason why uniformity is bizarre and not really true. I mentioned briefly before, I'll remind you, unlike systems now, System R originally didn't keep low and high, it kept low 2 and high 2. Low 2 was the second lowest value, high 2 was the second highest value. You know why? Null was treated as basically minus infinity, as the smallest negative value. And you didn't want null to count as the lowest value, so it kept the lowest, second lowest, and the second highest, even whether the column had null or not null. These days, null is represented differently, including using the approach that you used in Project 1, but historically that's used. How many leaf pages are there in the index, which is important? How many levels there are in a B tree? You know, all kinds of things. The number of statistics that are kept inside the catalogs of systems these days, including performance characteristics, is huge. There are systems that have 40 different catalog tables or more. Some of them having to do with authorization, who's allowed to do what, some of them having to do with performance, some having to do with the structure of the database, things about stored procedures and functions, triggers, logs, rules, all kinds of catalogs. I mean, all the metadata about the database is stored in the database. Sometimes in slightly clunky form, sometimes not. Now, let's see what we can do about estimating cost. And we'll go back to what I said before. Cardinality does depend on the order in which you access the tables. It's important for cost not to depend. The cost of getting A, B, C, E shouldn't depend on how you get A, B, C, E. The cardinality, the cost can depend on it, but the size, the cardinality should not. And you'll see by the cost formulas that it's independent of how you get it. So these things, the absolute value sign is a way of representing the cardinality, the size of something. So assume that you have an equality predicate, the term is P is attribute A is equal to some fixed value, you know, val, or some expression value. And by the way, if you have a predicate, you know, A1 equals A2, and you already have A2 from a different table, then it's the same deal. I mean, once you have your neck around a tuple, then A1 equal that tuple's value is the same as having a constant. Right? That's how you do with joins and so on. So again, to be able to figure out what the size of the thing is, you figure out what the size of the relation you have is. And we want to find out what the reduction factor is if we have a predicate which says A is equal to a value. Well, you project on just that one attribute, getting rid of duplicates. This is just a notation, relational algebra, where we get rid of duplicates. So you look at basically the notation pi sub A of R means how many different values are there of A. Take the projection on A, get rid of duplicates, that's implicit here, and count how many values you have. How many different values are there for the column A? That's all that means. So implicitly duplicates are out. If they weren't, then it would just be the size of R. So if there are 10 different values, you get 1/10. If there are 50 different values, it's 1/50. If there are 100 different values, you would get 100th. If there are 13 values, it would be 1/13. So you take R's cardinality, divide by the number of distinct values of A, and that assumes a uniformity. That's a uniform distribution. So for example, if you select where employee equals 23, and you assume that there are 100 different ages, then the reduction factor would be 1/100th, so it would be the size of R divided by 100. Okay? And now, we already gave you an idea about what's going on there. Suppose that you have a range predicate. And there's a thing in SQL that I didn't talk about 180, but you can even write a between predicate in SQL. It says it's between a value. You could also say range greater, so age less than 50, you could say age greater than 73, or you could say age between 50 and 73. That's also legal in SQL. So you have a range predicate where it's between value 1 and value 2. And basically what you do is you basically take the size of R and you're going to multiply it by, and this formula is slightly wrong. And I keep saying that I'll change it, but I never change it because I like making the point about it being slightly wrong as opposed to just going ahead and using it. This formula is a little bit off. Maybe somebody can tell me why. But let me tell you the idea of the formula and then we'll talk about why it's wrong. A little bit wrong, but a little bit. Close only counts in horseshoes and hand grenades, as you've probably all heard before. So basically what you do is you say, okay, how many different values are there potentially, assuming that I just know about high and low. I take high minus low. So for example, if ages are between 0 and 99, that would be minus 90 minus 0. And if I'm looking for things between, let's say, 50 and 60, then I would say that there are 10 different values between 50 and 60, so it's going to be 10 divided by whatever it is, 99 or 100 or whatever. So the idea is, again, that you take the number of values divided by the overall range, and that's going to tell you what's going on. Somebody want to tell me what's wrong with this formula, or do I tell you? Go for it.
I believe it's off by 1 because it's less than or equal to.
Which one is off by 1?
It should be
the top of the numerator or denominator?
Numerator.
Both.
Both.
Okay. Let's go over the example.
Oh yeah, you're right.
Let's go over the example. How many different values are there between 0 and 99? Sorry folks, there aren't 99 different values, there are 100. So it really should be high minus low plus 1. How many values are there between 1 and 100? It's not 100 minus 1, it's 100 minus 1 plus 1. So it should be high minus low plus 1. And now, how many different values? Suppose that I'm looking for people who are in the 50s. So how many different values are there between 50 and 59? 59 minus 50 is 9, but there aren't 9 different values between 50 and 59, there are 10. So this should be val 2 minus val 1 plus 1, and that should be high minus low plus 1. So again, this is why I never fix it. It's just too great an example to go over in class and ask people what's wrong with it. So I'm not going to fix it. It's wrong. Now you know why it's wrong. Okay? So you basically take the range size with the plus 1s in there, and you divide it. You take the range of what you're looking for between val 1 and val 2, because they are both less than or equal to, which has to have the plus 1. And then you take a look at the high minus low, again, plus 1. And that tells you what's going on. And again, it assumes uniform value distribution for all the values between low and high, inclusive. Okay? And basically, if you're looking for a predicate where it's something like, a less than 50, or sorry, a less than or equal to 50, right? Then you use the low value, so you use val 1 to be the low value. So if the values are between 0 and 99, and you're looking for all the things where the age is less than or equal to 50, then you basically, it says the same thing as age is between 0 and 50. So if 0 is the lowest value of age less than or equal to 50 is the same as saying 0 less than or equal to age less than or equal to 50, equal value. And if you're looking for age greater or equal to 63, and the age values are between 0 and 99, it's the same thing as saying age greater or equal to 63 and less than or equal to 99. So even when you just have less than or equal to or greater than equal, you can go ahead and you can play with that based on that and get the reduction factor. So the reduction factor is this term, but one more time, but the numerator and denominator need a plus 1 introduced in them for this to be able to work. And at this point, I will switch over and give